A tank begins as a set of constraints that refuse to cooperate. It must weigh as much as a small house, carry a gun capable of punching through thick armor, protect its crew from direct hits, and still move across unstable ground without collapsing under its own mass. The manufacturing process is about forcing those constraints into alignment, step by step, until they function as one machine. The first stage happens entirely in design systems. Engineers build the tank as a full digital structure before any physical work starts. Every surface is defined, every internal space accounted for. The hull is shaped to balance protection and weight. The turret is sized to carry the main gun while maintaining stability. Internal compartments are mapped so that the crew can operate, the engine can breathe, and ammunition can be stored safely. The level of detail here is extreme. Mounting points for suspension arms are placed within tight tolerances because even a few millimeters of misalignment can affect how the tank handles terrain. The turret ring, which supports the entire rotating upper structure, must be perfectly circular and precisely seated. The path of the gun's recoil is modeled so it clears internal components during firing. Even cable routing is planned in advance to avoid interference with moving parts. Simulations push the design to failure before its existence. Impact models show how armor reacts to kinetic penetrators and shaped chargers. Structural models test how the hull flexes when crossing uneven ground. Thermal models track how engine heat spreads through confined spaces. Engineers adjust thickness, angles, and materials until the structure can handle these stresses without excessive weight. Once the design is locked, manufacturing begins with raw materials. Armor-grade steel arrives in large plates, often several centimeters thick. This material is not ordinary steel. It has been formulated with specific alloys and heat-treated to achieve a balance between hardness and toughness. Hardness resists penetration. Toughness prevents cracking under impact. Achieving both at once is difficult, which is why the production process is tightly controlled. The plates are cut using CNC-controlled plasma or laser systems. These machines follow digital patterns that match the design exactly. Cuts must be clean and accurate. A rough edge or incorrect angle can compromise how pieces fit together later. Openings for hatches, viewing systems, and mounting points are also cut at this stage. After cutting, some sections are shaped. Heavy presses bend plates into angled forms, where required. Angled armor is more effective because it increases the path a projectile must travel through the material. It also helps deflect incoming rounds. Forming thick steel requires significant force, and the process must avoid introducing cracks or internal stress. Heat treatment follows for many components. Plates may be heated to high temperatures and cooled under controlled conditions. This changes the internal structure of the steel, locking in the desired mechanical properties. If cooling happens too quickly or unevenly, the material can become brittle. If it cools too slowly, it may not reach the required hardness. The process is monitored closely to maintain consistency. Composite armor sections are built separately. These are layered assemblies rather than single plates. A ceramic layer might sit at the front to disrupt incoming penetrators. Behind it, metal layers absorb energy and contain fragments. Composite materials between layers help distribute force. Some designs include air gaps that reduce the effectiveness of certain threats. Each layer is cut, formed, and assembled into modules that fit into the tank's structure. With armor components ready, the hull assembly begins. Large sections are moved into position using overhead cranes. The weight of individual plates can be several tons, so precise handling is essential. The pieces are placed into fixtures that hold them at exact angles. These fixtures act as a rigid frame during welding, preventing distortion. Welding armor steel is a controlled process. The material's hardness makes it sensitive to heat. Before welding, sections are often preheated to reduce thermal stress. Welds are applied in multiple passes, building up strength gradually. Each pass must fuse correctly with the previous layer. Too much heat can weaken surrounding material, while too little can result in incomplete bonding. Robotic welding systems handle long, straight seams where consistency is critical. Skilled welders work on complex joints, adjusting technique based on access and geometry. The goal is a continuous, defect-free joint that can withstand repeated stress. After welding, the hull is inspected. Non-destructive testing methods check for internal flaws. Ultrasonic testing sends sound waves through the material to detect cracks or voids. Magnetic particle inspection highlights surface defects. Any issue found is corrected immediately. A flaw left in place could grow under stress and lead to failure. The turret is assembled in parallel. Its structure is built from a combination of cast, machined, and welded components. The shape is designed to deflect incoming rounds and house internal systems. The turret must also support the main gun and allow smooth rotation. The turret ring interface is machined with high precision. This is the surface that connects the turret to the hull. It must allow rotation while carrying significant weight and absorbing shock from firing and movement. Any irregularity can cause binding or uneven wear. The gun mounting system is installed next. The main cannon is supported by a cradle that allows it to elevate and depress. Recoil systems are attached to manage the backward force generated during firing. These systems use hydraulic or mechanical components to absorb energy and return the gun to position. Alignment is critical. The gun must move smoothly and maintain accuracy. With the main structures complete, attention turns to the powertrain. The engine, transmission, and cooling system are combined into a single unit known as a power pack. This module is tested before installation. It is run under load to verify output, temperature control, and reliability. Sensors monitor oil pressure, coolant flow, and vibration levels. Installation into the hull requires precise alignment. The engine bay is compact, leaving little room for error. Mounting points must line up exactly. Cooling systems are connected, including radiators and fans designed to manage heat under demanding conditions. Air filtration systems are also installed to protect the engine from dust and debris. Fuel systems are integrated at this stage. Tanks, pumps, and lines are fitted and sealed. The system must deliver fuel reliably while preventing leaks. Safety features are included to reduce fire risk. Below the hull, the suspension system is assembled. Torsion bars are installed across the width of the hull. Each bar is connected to a road wheel through an arm. When the wheel moves upward, the bar twists, providing resistance and absorbing energy. These bars are made from high-strength steel and must withstand repeated stress cycles. Road wheels are mounted onto their arms and aligned carefully. Shock absorbers may be added to control motion, especially at points where loads are highest. Drive sprockets are installed to transfer power from the engine to the tracks. Idler wheels and return rollers guide the track along its path. Tracks are assembled from linked steel segments. Each segment is designed to handle wear and impact. The links are connected to form a continuous loop that wraps around the wheels. Track tension is adjusted to ensure proper engagement. Too loose and the track can slip. Too tight and it increases wear and resistance. With mobility systems in place, the track can move under its own power. Next comes the installation of weapons and control systems. The main gun is lifted into the turret and secured within its mounting system. The breech mechanism is fitted, allowing rounds to be loaded and fired. Recoil components are connected and tested for smooth operation. Stabilization systems are installed to keep the gun steady during movement. Sensors detect motion, and control systems adjust the gun's position in real time. This allows accurate firing even when the tank is moving over uneven ground. Fire control systems are integrated next. These include optical sights, thermal imaging devices, and laser rangefinders. A ballistic computer processes data such as distance, movement, and environmental conditions to determine the correct aiming point. The system must respond quickly and accurately. Wiring these systems requires careful routing. Cables are secured against vibration and protected from heat. Connectors are sealed to prevent moisture ingress. Each circuit is tested to ensure proper function. Communication systems are installed to allow coordination between crew members and external units. Radios, intercoms, and data links are integrated into the tank's network. Final assembly adds remaining components. Armor modules are fitted into place, completing the protective shell. External equipment such as storage bins, machine guns, and smoke launchers are mounted. Crew stations are installed, including seats, controls, and displays. Ammunition storage systems are secured with safety features designed to direct any internal explosion away from the crew. At this stage, the tank appears complete, but it has not yet proven itself. Testing begins inside the facility. Systems are powered on and checked individually. The engine is run through different speeds. The transmission is tested for smooth operation. The turret is rotated through its full range. The gun is elevated and depressed. Electronics are powered and monitored. Leaks are checked, temperatures are measured, Noise and vibration are observed. Any issue is recorded and addressed. The tank then moves to field testing. Mobility trials push it across rough terrain. It climbs slopes, crosses obstacles, and drives over uneven ground. Engineers monitor how the suspension behaves and how the engine performs under load. They look for signs of stress or wear. Live fire testing evaluates the weapon systems. The main gun is fired to confirm accuracy and recoil performance. Stabilization systems are tested during movement. Fire control systems are checked against targets at various distances. Testing is repeated as needed. Problems are fixed and the tank is tested again. Components may be inspected for early wear. Adjustments are made until performance meets requirements. Only after passing these stages is the tank considered ready.